Hi, and thank you for inviting me. I know it's the last talk, so I'll do my best to make you stay awake. I'm going to give an overview of using satellite observations for environmental modeling, and tomorrow we will hear two talks about more modeling approaches using satellite data. But before I start, I want to share with you how I got connected to environmental research. 20 years ago, I thru-hiked the PCT, the Pacific Crest Trail, going from the border of the US with Mexico to the border with Canada, walking and living in nature over 2,600 miles. This experience taught me a lot of things, but mainly two things. One, we are very small compared to the environment. And the second thing is that that's what I want to do when I grow up. I want to develop tools that will enable us to know more about the environment. So I invite you to join me for a short hike and to observe Earth from space. We're recognizing 62 years since the first launch of an Earth observation satellite. And since my talk has a very different terminology than the previous ones, I'll give a short background about remote sensing and satellites. I'll focus on air quality applications and some others, and finish with a summary of the capabilities and limitations of using satellite data for health studies. There are two main types of satellites. One is the LEO, low Earth orbit satellite. 60% of the Earth observation satellites are LEO satellites. They constantly move relative to the Earth, so they have a daily global coverage, and they overpass the same location at a certain time of the day. Their temporal resolution is once to twice a day, and their spatial resolution is on the kilometer scale. Goes from 1 kilometer and beyond. The geostationary orbit is way above Earth, so while the LEO satellites are on average located around 700 kilometers from Earth, the geostationary satellites are around 36,000 kilometers from Earth, and from that point of view, they're looking at a fixed area. So they observe the same area every day, and their temporal resolution is very high, so they provide data every 5 minutes, 15 minutes, or 30 minutes. As I said, the spatial resolution varies depending on the satellite and depending on the sensor. It can go from 30 meters from Landsat through 1 kilometer products on water or air and up to 100 kilometers. The use of the products depends on our goals and on the application. Interestingly, I found that there are over 2,200 satellites up in space, and 150 of them are Earth observation satellites. So as you see, this is a very, very short list of satellite and instruments that have been used in environmental and health research using satellites. The list in black is current operational satellites and instruments, and the red ones are future instruments and satellites. The initial use of the data from satellites leveraged the global coverage that they supplied for global applications. And as previous talkers said, there is no climate change, but we can see from satellites that the year 2019 was shown to be the warmest year on the global surface temperature since 1880, so 140 years of no climate change. Following global applications, I will talk today on more local and regional applications in environmental research. Satellites have been used in many fields: agriculture, disaster management, weather, water resources, and ecological forecasting. Today I will talk about air quality and public health use. So this is a short list of different products. I'm not going to go over all of them. The takeaway I want you to learn from is the different fields. So the first brown list is different products that are related to aerosols and air quality. And they're on the kilometer resolution, and from LEO satellites, we can observe them 1 to twice a day. The green NDVI and evapotranspiration are used for greenness and ecology studies, and they can be found from 10-meter, 30-meter resolution and up to 25 kilometers. Depending on the satellite and the sensor, they can be observed between 1 to 16 days. Similarly, excuse me, the land surface temperature, which can be found in different sensors and satellites, can be, is observed from as high resolution as 30 meters up to 1 kilometer every 1 day or 16 days, depending again on the sensor. The red group is variables that are derived from thermal bands, like fire detection and nighttime light, which we just heard about. And they also are varied in their spatial resolution. Satellites give us two main products: the data, but also imagery. And today we can find imagery with a very high resolution from commercial satellites in the resolution of 0.5 meter, up to 250 meters from NASA satellites. There is only one satellite today that can give us the vertical distribution of aerosols. I won't talk about it. It has a very poor availability in time and in space, and hopefully in the future we'll have more information about the vertical distribution. So what else can satellite retrieve that maybe the air quality community is more interested in? We see signals of ozone, nitrogen dioxide, sulfur dioxide, formaldehyde, carbon dioxide, methane, and aerosol optical depth. Yes, PM is not here because it's not directly measured from space. These are all retrieved products. And a very quick remote sensing introduction. So what we see here in the figure is the sun, which is the source of light, and the light beam hits the surface and then reflects basic physics, and the energy of the light gets or arrives to the satellite. But in the atmospheric column, we have aerosols and we have gases that absorb and reflect this energy. So the AOD reflects the absorption and reflection from these aerosols and gases that is reduced from the sunlight and arrives to the satellite. How does AOD look like? This is an image of Lagos, Nigeria. This is a satellite image, a 1 kilometer AOD product in 550 nanometers, showing a monthly average of relatively high AOD. This may come from dust event that covers Lagos. A month after that, the rain cleans the dust, and we can see much lower AODs. But is it a direct relationship between what the satellite sees and what we observe on Earth? So 3 things about satellite retrieval limitations. 1, it's an integration of the whole atmospheric column. 2, it's limited by cloud cover. So when we have clouds, we don't have retrievals, usually. And the third one, in LEO satellites, it's a snapshot. So we have one observation once a day. So we heard about this a little bit previously. Why are we interested in PM, and how do we connect PM with satellite data? So PM2.5, fine particulate matter, has a very, very increasing literature on associations with adverse health effects, especially with cardiovascular and respiratory diseases. The HEI State of Global Air Report in 2019 showed that the total air pollution is the 5th cause of death globally, while chronic exposure to ambient PM2.5 is attributed to almost 3 million deaths in 2017. The burden of disease 30 years ago showed that diarrhea and infectious disease was the first cause of death or losing years of life. 30 years after that, the cardiovascular disease is the first cause of death, and thanks to advances in health, diarrhea is not on the list anymore. So until satellite data has been used in epi studies, exposure matrices were based on ground networks, which in places can be sparse or even not exist. Satellite have the capacity of a very large spatial coverage and spatial and temporal patterns that ground networks, which are point measurements, don't provide. So many studies that look at the association between AOD and PM are adding more data, like meteorological data, land use, transportation, in order to create an air pollution exposure history database for better exposure matrices for public health studies. This is the current status of ground PM 2.5 monitoring network from the OpenAQ database. And on the bottom right, you can see the map of the population density, the current population density in the world. What I want to point here is that in a lot of places where the population is very dense, like in Africa, for example, we don't have monitoring network. And that's where satellite data can give us information that we don't measure and we don't know about. Interestingly, in the United States, which is the country with the most complement monitoring network, still 31% of the population is not covered by PM monitoring stations. So I'll start talking now about satellites, different satellites and different studies that use them. The first one is MODIS, Moderate Resolution Imaging Spectroradiometer, which is an instrument launched on 2 satellites. It's on board the NASA's Terra and Aqua, and we have data from MODIS since the year 2000. It has 36 spectral bands, 7 of them are used for aerosol variables, and it has 3 different AOD algorithms and 3 different resolutions, 1 kilometer, 3 kilometer, and 10 kilometer. MODIS has been widely used for PM modeling in different places in the world, and I did a quick search in Google Scholar for the words MODIS and PM 2.5, and since 2000, where we only had a couple dozens of studies, we see a significant increase in the number of publications using this data source. And we expect this to grow, although MODIS, Aura, and Terra, Aqua and Terra are expected to go off orbit in the next couple of years. But the data is still there. So this is a very short list of studies. What I wanted to show here that they really cover different places around the world. All these studies look at AOD-PM relationship, and they use very different statistical methods, from multivariate regressions, mixed effects models, generalized additive models, and then going a little bit into the machine learning world with SVMs and random forests. What I see from this observation, looking at so many studies, is that this is a very local phenomena, the association between AOD and PM, based on the local climate and environmental characteristics. So how does it look like? This is an example of a study done in my home country, Israel. You see an RGB image on your right and on your left, and then you see the MODIS 10-kilometer AOD on your right. What you see here, the triangles represent the point locations of the PM2.5 and PM10 stations in Israel. These are the points where we have data from, but that doesn't give us any information of what's going on, what's the air quality between the stations and outside, because so many locations you can see spatially are not covered by these stations. This is the 1-kilometer MODIS AOD product called MAIA, and it provides a continuous map. We can calibrate a model using the MAIA AOD and their ground stations, and then apply this model to all pixels where we have AOD but don't have PM data. Using Professor Klug hybrid model, using additional spatiotemporal variables, we calibrated and validated this model over Israel and created daily maps, continuous maps of PM2.5 and PM10. These exposure maps can then be used in health studies and improve the spatial coverage and spatial resolution from what they have used until now. The next satellite or instrument I want to talk about is the multi-angle imaging spectroradiometer called MISR. And one big difference from MODIS is that it has 9 view angles that enable to obtain more information about the aerosols type and composition and characteristics. It has a currently new algorithm with a 4.4 kilometer resolution, and it's also on the Terra spacecraft, so we have data since the year 2000. I'll present 2 studies I was involved in. The first one was in Ulaanbaatar in Mongolia. I don't know if you know, but this is one of the coldest areas, or cities in the world, and also one of the most polluted areas in the world. Their winters, it's located in a valley, so it captures all the pollution, especially in the winter, where they have about half a year of snow, and the main source is coal burning and biomass for heating and cooking. The dots on the map represent the PM monitoring stations, so they don't have much, but they have a lot of health issues and not a lot of interest from the science community. So since we have a student there that was able to gather health data, our first step was to be able to develop a model based on satellite data to know spatially what is the air pollution or air quality during the different seasons. So here we tried both MODIS and MISR data, and since they have over the winter a lot of snow, MODIS wasn't able to retrieve data because snow is a very bright surface, and that's one of the limitations of the availability of MODIS AOD. MISR, because of its different angles, was able to provide us with more AOD data. And we tested different models here and found that the SVM gave us the best predicting model, again validated with the limited network, ground network that we had. And the images that you see up there is the top image is the PM2.5 predicted map for the summer, so very low concentrations. And on the bottom is the winter PM concentrations. The upper red area is where the citizens or locations of human activity, and the bottom red area are coal mine plants. I do want to mention that this is such a polluted city that the concentrations measured in the ground stations exceed 20 times the WHO guidelines. And our next step is taking our model and associating it with health effects and hopefully help them make progress in regulations to reduce the air pollution sources. The next study I'm going to present was done in California and also used MISR data. This is data that was gathered through the Dragon campaign, which is a campaign in a very small spatial region that has satellite data, PM 2.5 data, and AOD measured from ground stations called AERONET. So the circles here represent the co-location of the AERONET and the PM 2.5 stations. And what we try to do is to see if we can calibrate models based on ground-based AOD to predict PM, and then apply these models to satellite data. And this was in purpose of a future mission that I'll talk about in a second. This is the Central Valley of California, and this is one of the most polluted areas in California. And what you see in the background is the MISR-based predicted PM 2.5 that was able to capture this Central Valley pollution based on the model that we calibrated without satellite data, only with ground AOD data. And we see that we had good agreement and relatively low error, both when we calibrated the model with AERONET and then when we validated it with MISR data. The future mission that I was talking about is called MAIA, and this is the first mission from NASA JPL that its purpose is environmental health. The science team meeting includes aerosol scientists, but also epi-scientists and public health researchers. And the MAIA is going to combine the capabilities both of MODIS and MISR and provide 1 kilometer PM modeled data in addition to AOD, which is the first time this is happening. MAIA is planned to be launched in about 2 years, and it's going to be a 3-year mission. Compared to MISR and MODIS, it's not a global coverage. It's looking only in specific target areas, and in each of these locations, they're putting ground monitoring data for PM 2.5, PM 10, and speciation of PM, which is another unique data set that we don't have from other missions. Those data sets will help calibrate the models, and the different locations are very different in their environmental characteristics, going from relatively clean areas like in northeast US with a mean PM 2.5 concentration of 9 micrograms per cubic meter, going to China and India, which have over 100 micrograms per cubic meter, which is way over the WHO guidelines for exposure. Moving on to OMI. OMI is a hyperspectral instrument on the AURA satellite, and on top of also providing AOD, it gives us gaseous pollutants like NO2, SO2, and ozone. And due to the UV bands, it provides data on absorbing and non-absorbing aerosols. NO2 the main source is traffic and industry activity, and there has been a study showing that environmental legislation reduced the NO2 emissions, and you can clearly see this on the map. And I'll let the short movie explain a little bit more about the SOMI capability.
Nitrogen dioxide is a gas emitted during the combustion of fossil fuels. It's released from the tailpipes of cars and the smokestacks of power plants. Together, these emissions affect the quality of air we breathe. Since 2004, an instrument aboard NASA's AEROSOLS satellite has measured levels of nitrogen dioxide in Earth's atmosphere. In 2014, we released satellite images that show how environmental regulations have led to reductions in nitrogen dioxide over major US cities. Now we created global maps that allow us to see how levels have changed around the world over the last decade. In Western Europe, despite the recent vehicle emissions scandal, nitrogen dioxide levels have decreased by as much as 50% due to tighter environmental controls. In China, we see an increase in levels over most of the country due to a rise in coal use for power generation, but decreases for some cities like Beijing, where a growing middle class is now demanding cleaner air. In the Middle East, we see decreases in nitrogen dioxide levels over Syria due to the country's civil war and displacement of its population. Meanwhile, levels have gone up in neighboring countries where millions of Syrians have taken refuge. In the US, the only increases are in regions with intensive oil and natural gas extraction, including fracking. In North Dakota and Texas, we see increases of 30% in some areas. By monitoring levels of nitrogen dioxide from space, we can see and quantify the effects of things like energy usage, environmental policy, and even civil unrest on air quality across the globe.
So he spoke about China, and I found this a couple of days ago in the news, and I thought it's quite interesting. So usually the pollution levels in China are represented here, which are very, very high and exceed all the guidelines, the relevant guidelines. And usually every new year, their new year occurs at the first week of February, you see a very clean image of pollution. But this year, due to the coronavirus, the maps are remaining clean. And NASA is continuing to follow this, and due to the lockup and no factories and no transportation, coronavirus is out there, but at least they're breathing much cleaner air. I don't know what's the cardiovascular rate mortality now, but maybe that's worth checking. Another interesting study using SOMI data is mapping cancer risk from formaldehyde. SOMI is the first satellite that was able to give information about formaldehyde that is poorly monitored on Earth. So this study from 2017 was able to map the occurrence of formaldehyde and then use that to map the cancer risks in the United States. And one of the reasons that the Southeast has more risk is because the formaldehyde is naturally atmospheric source from oxidation of an organic compound that is emitted from trees that are located, most of them in Southeast US. So I didn't mention about the SOMI that it has very unique variables, but it has a very coarse resolution of 13 by 24 kilometers. In 2018, the trope SOMI on the Sentinel 5P from the European Space Agency was launched, and it continues the SOMI legacy, providing very similar variables, just in a much higher resolution of 7 kilometers. The algorithm developed was in collaboration with NASA. And as an example, you can see here on the right, you can see the SOMI data, and on the left, the trope SOMI over the same area. And you can see, that the trope SOMI gives a much better spatial coverage, and also you can see the spatial variation that wasn't enabled in the SOMI data. I'm going to continue with the SUOMI-NPP. And on the SUOMI-NPP, there's the VIIRS instrument that also provides AOD. And it also has several algorithms, which I'm not going to talk about. I will mention two products. One is the Blue Marble, which gives images of the Earth in a spatial resolution as high as 500 meters. And the second one is the Black Marble, which provides the nighttime light in a relatively high resolution of 750 meters. And we'll see another short movie and look into some socioeconomical uses of this product. Oops, sorry. Okay, it's not working. So I'll talk about two studies shortly that I found interesting. One of them came out of a group at Stanford, and they wanted to look at poverty, spatial distribution of poverty in developing countries in Africa. And there is no much data about it. We have more surveys and data in developed countries, and they thought, what public available data can we use in order to have a spatial map of the poverty in those areas? So they combined daily satellite images and also used the VIIRS nighttime light product in order to predict poverty, and pretty successfully in African locations. Another study in China used the nighttime light product and looked at the association with social media uses to derive human population dynamics. And the map here shows that this correlation has a very clear spatial pattern in the different settlements and the city center. So I mentioned the Blue Marble, talking about imagery, and I want to present a project that we're doing with a commercial suite of satellites from Digital Globe, which provide satellite imagery in a very high spatial resolution between 0.5 meter and 3 meters. They have 6 satellites and provide data on a daily basis. And now we took a totally different point of view trying to predict PM and NO2. We're not trying to do statistical modeling between two different data sets, but we're trying to connect images and objects in the images that represent the urban environment to the PM or NO2 pollution in a certain place. For that, we used a deep learning approach, and we're looking at a hybrid approach that takes 2 different branches into account. One is an object classification branch, and the second is a physics-based branch. And our results over London are promising. What you see here is our prediction maps on a 100 and 200 meter resolution, capturing for the NO2 the roads, for example, and you see the annual mean for each one, so our prediction error are pretty low. For the PM, it's about 6% relative error, and for the NO2, about 13%. And we have a poster on this, so for more details, you can come to our poster tomorrow. We think this is a pretty exciting model, and our goal is to be able to transfer this model to developing cities in Africa. I need to go fast here, so I'll jump here. One question that we have related to the temporal resolution of LEO satellites is the fact that they don't capture the daytime variation because it's a 1 snapshot a day. So one question we had is, what is the best temporal PM measure to use in health studies? We use 24-hour average, but do we breathe average air? So the upcoming geostationary suite with satellites giving very high temporal resolution products might be able to use that to answer this question. And since I have one more minute to talk, I'll just show you this map. This is an international collaboration suite of geostationary satellites over the globe that will provide, in the next 2 or 3 years, some of them are already launched, data related to the environment and aerosols. And they're all going to be on the GeoNext, which is developed at NASA Ames, which will be a fixed grid for geostationary data. And this is how geostationary data looks like. This is a land surface temperature on a 10-minute resolution, capturing a heat wave in Australia. So this is something we definitely wouldn't be able to capture with LEO satellites. I'm going to jump over this project, which is in collaboration with Mount Sinai, just saying one sentence, using ecostress data, 70-meter data from an instrument on the ISS to be able to develop a high-resolution model to predict West Nile virus in Suffolk County. And since I need to finish up, I'll say that there are many satellites and instruments out there. They have their main advantage is their spatial coverage and their point of view, enabling to see things that we weren't able to see before. 20 years ago, we knew so little about our globe, limited with ground networks and in situ measurements. And satellites enable this new point of view, discovering new findings, new understanding and processes of the environment and the atmosphere. The field will continue to grow and develop, recognizing the geo-platforms that will create a new era of big data and new temporal resolution of satellite and ground data associations. And despite all the well-known limitations, satellites have been shown to be a very strong research tool for communicating environmental conditions and used in environmental health studies, especially for air quality, in the past, current, and I'm sure in the future. Thank you.